Welcome to another podcast. This episode, we're going to be taking a look at some of the language and terminology associated with not only this course, but all of partial differential equations and kind of applied mathematics in general. We're going to start by defining what it is we're going to be looking at this semester. And we're going to say, let's let U denote a function. And it's an unknown function of two or more variables. And those variables are usually t for time. And then you have variables like x, y, and z, which we will refer to as spatial variables. Throughout the course, we're going to assume that u of, and I'll just say u of x, y, z, t, that's how we would write it. We're going to assume that this thing is nice. Now, nice is kind of a loaded word, so what do I mean by that? Well, we're going to assume that it has certain continuity properties so that we can say the following. Anytime we have mixed partials, like say ux, y, we're going to assume that that's the same as uyx. In other words, the order in which you differentiate mixed partials doesn't matter in this course. Also, we're going to look at, if you had, let's say, a third order derivative here, something like uxxy, that's going to be equal to uxyx, which would be equal to uyxx. So by saying nice, what we mean is that mixed partials are equal. Now, we kind of need that for a lot of the techniques that we're going to do in this course. Fortunately, that is not that stringent of a condition. A lot of the functions that we'll be working with will meet that condition. It's just a continuity condition. So I want to take some time, since we have this set up now, to define some terms. The first term I want to define when we talk about an equation is what is the order of that equation. So the order of a partial differential equation is the highest order derivative. So for example, we would say a PDE is second order if the highest derivative in the PDE is a second order derivative. All right, the next term on our list here is linear. We've experienced a little bit of linear in ODE, but linear becomes even more important in PDE. Solving nonlinear PDEs is a nightmare. By linear, we mean a PDE is linear if the unknown function, that would be u in this case, if the unknown function and its partial derivatives appear at most once in each term of the equation. So what we mean by that is for each separate term, there can only be one u term in that term. So you can't have things like u times the derivative of u. That would be nonlinear in that case. So if it fails to be linear, then you're nonlinear. The other thing is that all u terms are of first degree. What that means is we can't have things like u squared, the square root of u, only u to the first power. The same thing is true of the partial derivatives. I can only have the partial derivative u sub t, let's say, or the derivative of u with respect to t. I can only have that to the first power. I can't take the square root of it. I can't square it, anything like that. All right, the third term that we're going to deal with frequently is the concept of dimension. So we say the dimension of a PDE is the number of spatial variables. So if you have 2 spatial variables, it's a 2-dimensional problem. 3 spatial variables, it's a 3-dimensional problem, and so on. Okay, 4th term here is another term that carries over from ODE, and that is the term homogeneous. And it means the same thing here, but probably the easiest way to describe it is that every term of the PDE includes the function u or one of its derivatives. So you're going to see how that makes for a really good definition here in a second. All right, what I have for us now is basically we're just going to look at, over here on the right-hand side, a couple of examples of PDEs that we will see throughout the course. And what I wanted to do is take a moment and basically define what these are in the language that we've sort of set out here in terms of order, linearity, dimensions, and homogeneous or not. We're going to start with the first equation. I'm going to name these first so that you know what these are. This is the wave equation. And for the wave equation, what we would say is that because the highest derivative here is a second derivative, we would say that this is a second order linear. Now we're looking at dimension. The dimension of this is based on the number of spatial variables. All we see in terms of spatial variables are x. So this is a one-dimensional wave equation, second order one-dimensional wave equation. And finally, in terms of homogeneity, every term of the PDE includes a u term. So you can see here I've got u in the first term, u in the second term. So this is indeed homogeneous. Okay, on to the next one. This is also the wave equation. Now, what makes it different from the one we just considered is, yes, they are both second order. You can see that all of the derivatives, in fact, here are second order. 2 derivatives, 2 derivatives, 2 derivatives. It is linear. It is 2-dimensional, however, because it includes both spatial variables x and y. So we would say that that is the 2-dimensional wave equation. And it is also homogeneous. Okay, next up is a slightly different equation. This is the heat equation. And it is also second order. You have to be very careful here. It's second order because the highest derivative is a second derivative in the problem. So it's a second order linear, one-dimensional homogeneous PDE, just like the wave equation is. And we're going to study heavily both the heat equation and wave equations throughout the semester. The next one's a little bit different. If we had to give this a name, I would call this a nonlinear transport equation or nonlinear advection equation. So right there we know this is going to be nonlinear based on the name. If we talk about the order, though, this is a new one for us. I would consider this to be first order. This is a first order PDE because the highest derivative is 1. You've got u, partial derivative of u with respect to t and the partial derivative of u with respect to x, but only one time is the derivative taken. So it's a first order problem. It is nonlinear, and it is nonlinear because of this term right here. Remember, our definition of linearity is the unknown function and its partial derivatives appear at most once in each term. And if you look at this term, you've got 1 and 2 parts of it that involve u's, and that violates the definition of linearity. So it is indeed nonlinear. This term has no u, and because that term has no u, if you look at our definition of homogeneous, that would make this an inhomogeneous equation. And then finally, the one that we left out here is the dimension. You can see that the x variable is the only spatial variable here, so this is a one-dimensional equation. Finally, on this last one, even though there are 3 terms, there are only 2 derivatives that are being taken here. And so it is still a second order equation. It is linear. It is homogeneous. But it is a 3-dimensional problem because we have 3 spatial variables, x, y, and z. And in fact, this is a really important equation known as Laplace's equation. And I want to take a second to talk about Laplace's equation and just sort of the dynamics of the Laplacian in general. If you look at the term uxx plus uyy, that term occurs frequently throughout the problem, this problem. You can see it right here, and we give this the notation delta u. So this is called delta u, which is the Laplacian of u. Now, some people will write this as the second order Laplacian, or they'll use nabla squared. So all of these are representations of the same thing. But here you can see that there are 3 terms involved. And so this is also the Laplacian of u, which we can write as nabla 3 of u. The Laplacian and in general gradients and a lot of the things that you learned about in Calculus 3 are going to be parts of differential equations, or especially partial differential equations. And so, for example, I could look at Laplace's equation here, and I could describe this equation and simply write down just this. This is a perfect description of equation number 5, and from context you would have to figure out what is the order, what is the dimension. That can be a little bit tricky. Not everything will be written out nicely like it is in 5. You might have it condensed into terms, and that's almost necessarily so because you might have 6 or 7 spatial variables that you're dealing with, and you wouldn't want to drag all of that out. So we get very used to these sort of condensed notations over the course of the semester. It's going to be really important that we try to make sense of these terms and use these terms frequently in class so that we're at least on the same page about what we're talking about. All right, we're going to deal more with this in class throughout the semester. Like I said, I'm going to try to use this language when I talk about PDEs with you, but I wanted you to know what some of the terminologies and some of the assumptions are that we're making for this course as we start to look at PDEs in specific. All right, thank you for watching.